So guys, today this video is going to be a big one. We are going to discuss how LLMs work. We are going to make an inference engine. Well, actually not make an inference engine, but actually see how does an inference engine works. So we will be covering most of the topic. We will just be scratching the top. We won't be going super deep, but you will get pretty good idea of how LLMs work. So Odin is LLM inference engine in C++ that currently I'm working on. And so first let's go on to the blackboard. So how LLMs actually work is, so first of all you have to know what gguf files are. These are called gov files. These are just the files that contains the model info. Along with the model info, they contain the actual weights, so the tensors, the weights that the LLMs use inside their matrix. So think of LLMs as just some big matrix that takes in your prompt, converts it to an integer array, so like integer array of some ID, token IDs, multiplies it with some big matrix and outputs another big array of token IDs and converts it back to words, and you get the answer response. That's how it's done. This big matrix has to be trained. So what training actually does, this big matrix contains so much variables, and you actually take a huge amount of prompts and their actual answer, and you change these weights in such a way that the prompts and the answer start to align to each other. And when you have fine-tuned these variables, so many variables, and after fine-tuning you have to store this variable in a file that's called a gov file. That's it for the gov file. Now these weights are actually floating point, but we actually store them in different quantized format like int 8 or q q1 q4 q4 k and so on. So why you have to convert float to int? Suppose you are working with a 3.6 billion parameter model. 3.6 billion is 3.6 into 10 raised to 9. If you multiply this by the size of float, that's 4 bytes, you are getting around 14.4 into 10 raised to 6, no, actually 10 raised to 9, 10 raised to 9 bytes. That's 14 GB of the model. So you have to have 14 gigabytes of space for storing the model, first point, and you have to have 14 gigabytes of the RAM to load the model in. So what researchers do actually is that they train the model and they quantize the weight. So quantization is just conversion of the weights in such a format that the size get reduced. So the Pi 3 mini that I am currently using as a test, so Pi 3 mini is around 1 billion parameter, so it gets around 6 to 7 GB of model size, and the quantized version is just 1 gigabytes in size. So we saved up RAM, we saved up hard disk space. Now you have to actually convert. So let's start with how gov files are loaded. So gov files are passed by gguf parsers, and we won't be going into deep, it's such a vast topic in itself. just consider that somehow we are able to get the tensors out. So these tensors are of different types. Some may be of float, some may be of Q4K, some may be of Q5K, and so on. You could actually see that on model info. Okay, so if I go down and if I just see for the layer 31, so I'm be showing you this. So it's layer 31 attention norm weights, it's of F32, means float 32. The 31 F down weights are actually forward pass down weights are Q6K quantized, it's Q4K quantized, Q4K quantized, and so on. So there are different quantization within a same file, so you have to dequantize these models. So how do we dequantize these models? Well, we use these things. So let me just go and show you the structure. So the structure of Q4K block is something like this, and you don't need to study these structure right now. You just need to have an upper look over what these things are actually saying. So if we will dequantize these tensors into float, suppose we dequantized these into float, the model will expand size obviously, so we will be getting a large model after dequantization. Suppose the model is of 7 GB after dequantization. So this defeats the purpose of quantization. Quantization not only allows us for a smaller file size, it also allows for more number of weights to travel in the memory bandwidth. So suppose your memory bandwidth, suppose 32 bytes at a time. It's really low, but suppose that's the case. 32 bytes is the maximum bandwidth that you could get. If you're going to store 4 floats, if you're going to use floats, that's 4 byte size, you are only going to get 8 floats through the memory, and memory access is 700 to 800 cycles slow. So you will be having so much time wasted in just retrieving the floats. So what we can do, we can quantize this can be of 6 bit, one weight of 6 bit, that's the Q6. So Q6 is actually 6 bit, it uses 6 bit. Q4 uses 4 bit, Q5 uses 5 bits. So now if you are using suppose Q4 quantization, so you can retrieve the model and each weight is just 4 bits in size. Each weight is just 4 bits in size. You fetch 256 weights at a time. For different quantization model, this is of different size. So suppose for Q4K, it's actually 5 bytes of the upper things and 128 this, so it's around 130 bytes in size, 256 weights. So you actually fetch the 256 weight worth of bytes from the memory, and on the CPU itself you quickly convert the quantized weights, that quantized tensors, to the dequantized version. So at max the tensors aren't dequantized and stored in the memory, they are dequantized on the fly. When you are needing to dequantize the weight, you are going to dequantize the weight, that's it. So we are storing less on the memory, we are having higher weights travel in the same bandwidth, so we are going to dequantize on the CPU. Now after dequantization, these 256 weight, suppose if each weight is of a single byte, that's int 8 quantization by the way. So if each weight is of single byte, you are having 256 bytes, and at max this 256 byte can expand up to 10 megabytes, 20 megabytes, but this 10 or 20 megabytes will live inside the L1 and L2 and L3 cache inside the CPU. So now you have gotten a great cache hit, and you will be able to perform matrix multiplication in a faster way. So you will be performing matrix multiplication in blocks of 256, because obviously we fetched the 256 weights. Let me just tell you how does this actually works inside the transformer. You will be needing a token vector of specific size. So for pi 3 mini, this size is 3072, and this x, for the very first time, before we feed the value x into the transformer, we have to put values in this. Okay, so this is an array and we have to put values in this. What are the values? Pi 3 mini or any other model provides us with something called token embedding weights. So token embedding weights right here. Okay, token embedding weights are the token to the actual vector. So okay, tokens are discrete values. Think of tokens as the discrete values, but if we want a continuous alignment between those discrete values, we have to map them into a continuous space. So I know it's going really high, but let me tell you this. So what we actually have is, we have to find a way to get super high association between the different discrete token values. So what do we do actually? We project them into a higher dimensional space. So for the projection, we have the token embedding weight matrix. So this matrix is of dimension 3072 by this thing 32,000. So what happens is, you are 32,000 in the number of rows, so 32,064 in the number of rows, and you are 3,072 in the number of columns. What you have to do actually is, for each and every token inside your prompt, you have to take the token, you have to take the text, convert it to a token, and use that token as an index to index the row that corresponds to this token. So the row at index token corresponds to this token. Now you have to take this row and copy this into the x vector that we had, that was 3072 in size. You know why? Because this row is of 3072 in size. So we have to take this, and this is the initial value of x. Now we have to normalize this. For normalization, Pi 3 mini actually uses RMS norm, root mean square normalization, and it's out of the scope of what we are going to learn, because it's mathematics, and it's basically, I'm just going to give you the straight up formula. It's basically this thing, and probability of x times x. Okay, so this thing is RMS norm. You don't have to learn about this. So we have to normalize this. Why we have to normalize this, you may ask? Because the x vector can have super high values and super low values, which may cause the gradient to actually either go super high, either explode to infinity, or to diminish to zero. We don't want both of this. We want our values to stay in a bound, and for that we have to normalize the x values to -1 over 1. RMS norm is root mean square norm, and it converts the value from -1 to 1. That's it. So any value from -infinite to infinite gets mapped to -1 to 1 using RMS norm. That's what you have to learn. That's it. So since we have now successfully gotten our x vector that's of 3072 in length and is normalized using RMS norm, we can pass this into our network. Each layer contains around 6, if I'm not wrong, let me just count, 1 2 3 4 5 6, yes, 6. So around 6 different matrices that you have to multiply your x value. Why we have to multiply? Let me just break it down really quick. Okay, so the first value is attention norm. Then we have the forward feed, up, down, and normalization. We have the attention output and the QKV weight. So what is QKV? K and V stands for key value pair. I don't know what Q stands for. So key and value pair are stored in the memory, and it is used for providing context of how the word changes. So QKV pairs are used to provide context. Suppose I have a word that has different meaning based on the context that it's used. Since it has different meaning based on the context, we need to provide the context, and the key value pair are the context that we provide. So now we have learned, or I should say now we have gotten an idea of how the transformer actually is working. LLM is actually working in under the hood. And if the thing that I explained is so naive, it isn't like, even I would not say it is 1% of what actually happens while you are trying to code an LLM inference engine. I would highly recommend to anyone who wants to learn about LLM to actually code an LLM inference engine in a systems language. So go code a LLM inference engine in Rust or in C++ or in C. And as a warning, you won't be getting enough information. So anything regarding the gguf files, anything regarding the model quantization, anything regarding the quantization format, you won't be getting information on that. You have to study the llama, and if you are not knowing what is llama, well, you have been living under a cave. So you have to study the llama.cpp inference engine, and you have to study specifically the ggml part of this. So this thing, you have to study the ggml part of llama, and it includes everything. So if I go and gguf.h, it includes almost every structure, almost every format that you would ever need of. Like you could actually search, I guess, Q4K, whatever it is. So this contains every format, everything that you would ever need, and the documentation is sparse. You won't be getting documentation, but you will be getting some explanation and some context regarding what the actual format or what the function or the structure is for. So that's nice, that's cool. And yeah, I have tried my best to explain you how an LLM inference engine works. That's it for today, and bye.